Okay, so now that we have some basic vocabulary under our belt, let's talk about the various ways we might manipulate matrices and vectors. The first operation we'll learn here is the notion of scalar vector products and scalar matrix products. So the idea here is that if I have a vector or I have a matrix, I can multiply that vector or matrix by any number I want, and the rule is deadly simple. So over here, I'm going to multiply the vector 3, 0, 4 by the number -7. And the rule for doing this says take every number inside the original vector and simply multiply it by -7. In this case, when we do this operation, we produce the vector -21, 0, -28. And the rule for matrices is exactly the same, except we have more entries to keep track of. So here I'm going to take the 3 by 2 matrix, whose columns are 3, 6, 2, 4, 0, 1, and I'm going to scale this matrix by 8. And all this means is that I'm going to take every entry in the matrix and multiply by the number 8. When we do all the arithmetic here, we end up with a new 3 by 2 matrix. And the entries now are 24, 48, 16, and 32, 0, 8 in the columns. We can also add vectors and add matrices as long as those vectors have the same size and as long as those matrices have the same size. So here I have two vectors in R3. The first vector is 2, 9, 7, and the second vector is 0, 6, 4. The rule for adding these vectors together says simply match the corresponding coordinates, add those coordinates together, and record the result. So the idea here is that 2 plus 0 is equal to 2, 9 plus 6 is equal to 15, and 7 plus 4 is equal to 11. So when we add these vectors in R3 together, we produce a new vector in R3. Again, the rule for matrices is the exact same, except we just have more entries to worry about. So here I have two matrices. It's crucial here that they have the same shape. Both are 3 by 2 matrices. And the rule for adding these matrices together says compare the corresponding entries, add them together. So for instance, when we add these two 3 by 2s together, we produce a new 3 by 2. Well, where did the entries in this new matrix come from? We matched corresponding entries and added them together. So this 17 here is in the 3, 1 position. So this is the third row, first column. We got 17 by going back to the original two matrices and adding the entries that are in the position 3, 1. So here we're adding 9 and 8 together to produce 17. So scalar products are simple here. We simply take a vector or a matrix and multiply every entry by a scalar. And addition is also simple. The only thing we have to worry about is that the things we're adding together have the same shape. And this is a crucial observation. In the way that we've set things up here, it doesn't make any sense to add two things together that don't have the same shape. So if somebody tried to write this sort of addition here, so here what we're indicating is something where we have a vector in R2 being added to a vector in R3, this makes no sense in the way we've set things up. Similarly, here we're trying to add a 2 by 3 matrix to a 4 by 2 matrix. This also makes no sense in the way we've set things up. So don't try to do anything like this. It doesn't make any sense. The next operation that turns out to be incredibly useful, albeit incredibly simple, is the notion of the transpose of a matrix. So the transpose of a matrix notationally is indicated by taking the symbol for the original matrix and then adding a t as a superscript. But what does that mean mathematically? Mathematically, this means that we're going to interchange the rows and the columns of the original matrix. So when we want to construct the transpose of a matrix, what we're going to do is we're going to take the rows of that matrix, rip them out, and put them into the columns of a new matrix. So let's see that in action here. I have a 4 by 3 matrix A, and the first row is 10, 17, 19. If I want to construct the transpose of this matrix, what this means is that the first column of the transpose will be 10, 17, 19. The second row of my original matrix is 1, -10, 11. To construct the second column of the transpose, I rip this row out and put it into the second column of my transpose, 1, -10, 11. And I keep doing this until I've run through all the rows. So the third row is -15, -3, 2. That becomes the third column of the transpose. And the fourth row is 9, 18, negative 17. That becomes the fourth column of the transpose. Okay, so that's a step-by-step procedure for constructing the transpose of a matrix. Let's take a look at what we've done here. Well, one thing to note is that the original matrix here was 4 by 3. However, we transposed this matrix and produced a 3 by 4 matrix. And this makes sense because what we are really doing is we're changing the roles of the rows and the columns. So the number of rows of the transpose becomes the number of columns of the original matrix, and the number of columns of the transpose is the number of rows of the original matrix. So in general, this applies. So in general, the transpose of an M by N matrix is an N by M matrix. Now, the transposes show up all over the place in math. It's actually kind of surprising, given how simple an operation is, how important it is mathematically. But it's also just useful for silly reasons. Here's an aesthetic reason why the transpose is a useful thing. By writing vectors as transposes of rows, I save vertical space. So remember, the way we've defined a vector is we've defined a vector as a vertical list of numbers. Well, the reality is I don't always have a lot of vertical space to work with when I'm writing, but I have maybe some horizontal space to work with. I can use the operation of transposition to communicate the exact same information while saving myself some vertical space. So the idea here is that vertical space is saved by writing vectors as transposes of 1 by n matrices. So here, let's say I'm working with the vector 9, negative 3, 4, 7. I can talk about this vector, but save myself some vertical space by writing this as the row 9, negative 3, 4, 7. But to indicate that I'm talking about a vector, I need to add this t superscript to indicate that I'm actually transposing this 1 by 4 matrix to produce a 4 by 1 vector. I like to call this horizontal notation, and we're going to use this a lot. So it's worth really staring at this slide and maybe writing down a few examples yourselves to make sure that you're comfortable interpreting rows transposed as column vectors. One useful property of transposition is that it's a linear operation. Whenever somebody says something is a linear operation, what they mean is that it distributes across sums and you can factor scalars out. So this is efficiently communicated in one equation. Let's say that we took two matrices of the same size, A1 and A2. Let's say we scale them by any numbers we want, C1 and C2, and add the results up. Well, that's a new matrix, and we could transpose that new matrix. And to say that transposition is a linear operation is to say that that procedure is the same thing as individually transposing the two matrices, then doing our scaling, and then doing our addition. So that's the exact same thing. So the idea here is that transposition distributes across sums, and we can factor scalars out. So linear operations are going to show up a lot in this course. Transposition is probably the simplest operation that we'll use that is linear, so I figure it's worth introducing that vocabulary now. An even simpler property that transposition has is that it's an involution. Involution sounds like an intimidating word, but it's actually a relatively simple concept. Involution means that if you do the operation twice, you get back the original input. So to say that transposition is an involution is mathematically to say that if we transpose twice, so A transpose transpose is just the original A. And if we think about it for a second, this should make sense, because if we transpose once, the original rows become the new columns, but then if we transpose again, those columns now become rows again. So transposition sort of undoes itself. Now that being said, there are matrices that are so special that if you transpose once, you don't change the matrix at all. And this is the notion of a symmetric matrix. Symmetric matrices will play an incredibly important role when we discuss the spectral theorem later in the course, but I don't want to do anything with them now, I just want to understand what they are. So a matrix is called symmetric if its transpose is equal to itself. So think about what this means. What this means is that if I construct new columns from the old rows, I don't change the matrix at all. So let's take a look at this example, which happens to be a symmetric matrix. If we look at the first row here, we're looking at -2, 17, -9, -1. And keep in mind, normally when we have some regular matrix, we might transpose the matrix and change the rows. But this matrix is cool because the first row here is actually equal to the first column, -2, 17, -9, -1. So the first row of S is the same as the first row of S transpose. So we're not changing the first row when we transpose here. And again, this is very special. Normally this wouldn't work. And not only does that work for the first row, but it works for all of the other rows. The second row here is the same thing as the second row of the transpose. The third row here is the same thing as the third row of the transpose. And the fourth row is the same as the fourth row of the transpose. So this is an incredibly special criteria. When this criteria is met, we call the matrix symmetric. Now, where does the term symmetric come from? The adjective symmetric refers to symmetry across the diagonal. So in order for this criterion to be met, what needs to happen is, well, we don't care what numbers we put on the diagonal, but once we establish the diagonal, we need all of the other entries to occur in pairs. So the diagonal of S here is everything in the 1, 1, 2, 2, 3, 3, and 4, 4 positions. Well, if you look at this -9, this -9 occurs in the 1, 3 position, and it's paired with this -9 that's in the 3, 1 position. If we look at this 30 here, this 30 is in the 2, 4 position, and it's paired with another 30 that's in the 4, 2 position. So symmetric matrices always work like this. You have any numbers you want on the diagonal, and then all of the other numbers occur in pairs that match up, which is why the matrix doesn't change when you transpose. So symmetric matrices are very special things, but they end up being really important matrices that play a really important role in things that we'll discuss later, like least squares problems and in the spectral theorem. So again, we'll do all that later, but for now I just want us to know what symmetric means. And another operation, which is relatively simple, is called the trace of a matrix. So the trace of a square matrix is the sum of everything on the diagonal. So here I have a perfectly good 4 by 4 matrix. Note, this matrix is not symmetric. One quick way to see this is this 5 in the 1, 2 position is paired not with a 5 but with a -5. Even worse, this 8 in the 1, 4 position is paired with a 12 in the 4, 1 position. So this matrix is square, but it's not symmetric. Which doesn't mean it's not interesting, but it just means that the adjective symmetric doesn't apply. So what is the trace of this matrix? The trace of this matrix is obtained by looking at the diagonal and just adding everything together. So the numbers on the diagonal here are -12, -19, 14, and 6. When we add all those numbers together, we happen to get the number -11. That is called the trace of this matrix. And one thing to note is that when we take the trace of a matrix, we produce a scalar, not a matrix and not a vector. So the trace of a matrix is some sort of scalar. And again, surprisingly, we'll see that the trace ends up being useful in certain instances. It sort of seems like maybe this is a silly operation, but it turns out to be important sometimes. And one thing about the trace is that this is another example of a linear operation. Again, what this means is that if I scale two matrices and then add those results up and take the trace, this is the same thing as individually taking the traces of our matrices and then scaling those results and adding them up. So we can distribute trace across scalar times matrix plus scalar times matrix in such a way that we can factor out those scalars.